Okay, thank you everybody for coming to the quantum gravity seminar. This week we're very happy to have Georgi Dvali tell us about memory burden effect in black holes and de Sitter. Go ahead.
Okay, yeah, thanks very much. It's a pleasure to I'm going to oh, sorry, this asks me. Okay, so yeah, it's a pleasure to give this talk, and so I'm going to discuss this general phenomena, so-called memory burden effect, and the consequences of this phenomena for different systems, in particular for black holes and for de Sitter space. These are my collaborators and in different sets of papers. Okay, so the initial goal of this research was to understand how black holes function, how they process information, and then it became very interesting on its own. This phenomenon. Then we realized that the phenomena is much more general than black holes. And so it has implications for many different systems, and it nicely puts the story in the unified way. So in certain sense, it shows that black holes are not special in some respects. Okay, so the black holes are the most compact objects of nature, as we know, and so they have the characteristic length scale, gravitational radius, and the radius of the horizon. And because they are most compact, they also carry their most compact stores of information. So they carry a hidden label, which counts the number of microstates. So it labels the number of microstates. So a classical observer that sees a black hole thinks it's one object, but actually in reality it's one out of exponentially large number of possibilities. And so these possibilities we can classify by entropy. We can account for them by microstate entropy. So I'm going to use microstate entropy all the time as logarithm out of number of states. And so one interesting thing about this entropy, a well-known thing, is that it scales like area. Okay, so it scales like area in units of Newton's constant, and this was source of a lot of interesting ideas and puzzles. So in particular, for example, long ago, Tost suggested that there may be some kind of holography, according to which because the way this entropy scales, it looks like as if you have like pixels on the surface of a black hole, and each pixel is like a qubit, and so yeah, you have this information that you have this entropy that scales like area. Okay. So question is, what's the physical meaning of this? Is this area law just a bookkeeping device, or is there really physics associated with it? Okay, so well, in particular, for example, if you take this Earth mass black hole, approximately the radius is a centimeter. So it has the entropy is like 10 into the power 66. So enormous number of degenerate macrostates. Now, in the situation in black hole physics, well, at least until some time ago, was very interesting in the following sense, that there are certain properties. So most of the well-accepted physics of black holes is within semi-classical treatment. Okay, so in the regime in which semi-classical treatment is good, we think we understand black holes pretty well. And in particular, there are certain features that everybody accepts, agrees on, but there is no understanding, there is no common understanding of what's the underlying quantum physics behind these features. Now, for example, here I'm listing some of the mysteries. Later will come more so-called mysteries, okay, quote unquote. So first is, as I said, the area law form of the entropy. Then semi-classically, these objects, they have information horizon, and then they evaporate thermally, with approximately thermally, of course. This is again only known in semi-classical approximation. And then there is a bound on the retrieval of the start of the retrieval of information advocated by Page, which is scales as actually it's entropy times the size of a black hole. So it's huge. This bound is huge. And so the reason why these are mysteries is because, for example, you say, okay, I have this object that has huge information, but then I have to wait, and then it decays, it emits energy, but I have to wait a really long time before I can even start reading decoding the information. For example, if you think about other sources of information, like if you think about the book, if I start taking pages out of the book and give you these pages, you can start reading it immediately. So, but for black hole, apparently this is not the way it works. Okay, and the question is why. Okay. Now, so the approach that I took to this subject, and this is the way I'm going to discuss in this talk, is that, I mean, whenever we have a phenomenon of nature, right, that we want to understand, let's say glass of water or something, and you see that this substance evaporates, and you want to understand what is this substance. Well, there are two ways to approach it, at least. The one is you can build a microscopic theory. You can say, okay, I mean, let me propose that water is made out of molecules, and molecules interact with each other, and they scatter and deplete, and water depletes. Or alternatively, you can just go and try to see if there are other substances which which have similar behavior. And if you find that there are other substances, in this particular case, there are other liquids, you discover that this property is not specific to water, and therefore there is some universal underlying phenomena behind these features. And that's the approach I took for black holes. Actually, it's really surprising that this was not done previously, because we could ask, so the question, how special are black holes, is an obvious question in a sense. It could have been asked 50 years ago or something, but it was not. And probably the reason was that we thought that the answer was obvious, because you say, okay, I mean, you say if I take a black hole and an apple, and let's say the black hole of the same size or of the same mass, it doesn't matter. I mean, of course, black hole is very special. Apple has nothing to do with this black hole. But this is also a meaningless comparison, because when we are comparing objects, we have to put these objects in the same universality class. And the question is, what's the universality class I should be thinking of? And the first thing I did, I defined the universality class, okay? So basically, my point was that let's try to compare objects in the following way. Suppose you have a quantum theory. So it doesn't have to be gravity. It could be anything, any other quantum theory, any other quantum field theory. Now, quantum field theory is characterized by two ingredients. First is the degrees of freedom, and the second ingredient is rules of the game, how these degrees of freedom interact with each other. And usually they are coupling constants that control this interaction. Now, we call them constants, but actually these couplings are not constants. They run. They run with momentum transfer or with the scale. So now you can ask this question. In a given theory, suppose I have a bound state or a soliton or any other object. I mean, it could be this chair, I don't know, planet, star, doesn't matter. And you can ask this question, what's the maximal microstate degeneracy that these objects can have within the validity of the given description? So within the validity of the given description means that you have those degrees of freedom as legitimate degrees of freedom, whatever they are, and they couple with coupling alpha. Now it turns out that there is a bound which can be written in two equivalent ways. Okay, one is given by the inverse coupling, inverse weakest coupling of the story that gives you the bound state in bound state. But the second form, which is the same actually, as I will explain, is more intriguing. So it turns out this bound, regardless gravity. Now, pay attention that we are not in gravity necessarily. This is also true in gravity, but in general. So it's always the area in units of a scale, of a Goldstone scale, if you will, of spontaneously broken Poincare symmetry. Now, this scale is uniquely defined for any object, because if you have an object that breaks Poincare symmetry, it's unambiguously defined, because anything that exists breaks Poincare symmetry spontaneously, any macroscopic object in particular. Correspondingly, there is always this scale, and this scale is the one that controls the entropy. So it turns out that the maximal entropy is given by the area in units of this Goldstone coupling. Okay, Goldstone scale.
Sorry. So can I ask one question about this?
Yeah, sure.
So if the system we have has two decoupled, like let's say there are two decoupled sectors, so there are some couplings which are set to 0 in some sense, and so then there's no bound on the entropy, or like I mean, what happens in the limit where the couplings go to 0?
If you have two separate systems and the couplings are 0, then independently they're going to obey this. Then this means that you are not really producing bound state between the two, because if you have two decoupled systems, then the bound state
I see.
can produce bound state in one, bound state in the other one, and formally can put them on top of each other. But this will be, yeah. So therefore, yeah, I mean, if you have an interaction that produces a bound state, no matter how weak interaction, then it counts. If actually it turns out, if I have time, I explain, because even in that case, if you have two completely decoupled systems, right? It turns out that this is perfectly meaningful, because if the systems are truly completely decoupled, then the one observer that deals with one system cannot really measure information of the other system. Then they are like fictitious. They're like two parallel, completely decoupled theories. The moment you have a device that can access information, this device necessarily creates quantum corrections which couple the two systems, and the bound gets restored. So yeah, so this looks like it's universal.
I see. So yeah, so there's a requirement that you can create the bound state in some sense. Yeah, I see. Okay.
Yeah, it's an example.
Yeah,
I mean, assume that you have a theory which has some object, some sort of bound state, sufficiently long-lived. I mean, sufficiently narrow resonance. Yes.
I see. Okay, and then can I ask one more question? So the scale F is set by the size of the object, or by some other? Yeah. What?
Yeah. Scale. So exactly. So the scale F. Yeah. It's of course the scale F is different for different objects, because it depends on the shape of the object and structure and so on. But if you take in the simplest case, if you take a spherically symmetric object with the uniform mass distribution, then it's given by the combination of the energy and the size. Yes.
Oh, energy and size. Okay. Yes. Okay. Thank you.
Thank you. Okay, so yeah, so this is basically what I was saying. Of course, in every system, when we have degrees of freedom and stuff, we have breaking of Poincare symmetry. For example, air in this room breaks Poincare symmetry spontaneously. Now, actually, a student of mine long ago corrected me that it was Lorentz, mostly it was coming from Lorentz breaking, the corresponding Goldstone. So yeah, and we have the sound waves, for instance, which are Goldstone modes of this. Okay, so basically, the most interesting ones are the objects that saturate the bound. Okay, so I call them saturants. The ones that have this maximal microstate degeneracy compatible with the validity of the description. Okay, by now we have huge number of examples. We have worked them through, and this story is very well established. Okay, let me give you some flavor of from where this bound originates, and actually it is intertwined with so-called species bound. Okay, now, so let me first give you this what I call universal species bound. So it turns out that whenever you have a system, and this system has certain number of degrees of freedom, relevant degrees of freedom for storing information. Okay. So this relevant, let me call them species, okay? So I have different species. Now, these species can be different fields, okay? Or they can be different modes of the same field, relevant for a given situation. And then there is a coupling alpha. So it turns out that there is a universal bound, again, within the given validity of the given description. We cannot go beyond it. So we cannot make, so n has to be less than 1 over alpha. Okay, so in other words, we can form this collective coupling n times alpha, which is 't-like coupling. I mean, 't formed a similar coupling in particular theory of large MQCD, large number of colors, but let me call it Toft coupling. Okay, so there's this collective coupling, and so collective coupling cannot become strong. Now, the fact that collective coupling cannot become strong within the given description, you can understand in several ways. And so one is, of course, loop expansion in Toft coupling breaks down. However, this breakdown is physical, because sometimes people think that this is like simply breaking down of perturbation theory. No, that's not true. If once the strong Toft coupling becomes strong, the breakdown is physical. This means that the theory changes the regime. And another way of seeing that, you can see that multi-particle amplitudes, for example, 2 to n processes, they start to be saturated at the so-called point of optimal truncation. Now, the point of optimal truncation is the most trustable point in this expansion with given degrees of freedom. And already on that point, which is not questionable, so the process becomes saturated by multi-particle states, which saturate this entropy bound. And so therefore, you cannot go further, because then otherwise you would break unitarity. And of course, you don't break unitarity. In reality, what happens is the theory changes the regime. Okay, so this is universal. Now, the bound actually originally was established in gravity. So now we call it species bound. From black holes, because from black holes is most transparent how you can see it, because in gravity, number of species is simply number of whatever degrees of freedom you have, because gravity couples universally to all the degrees of freedom. And they can see very, very easily by various arguments that actually for example, if you have a black hole of the inverse size given by the so-called species scale, and Planck divided by square root of n, and this is species scale in 4 dimensions. Okay, the farther than that, the decay cannot be thermal. Simultaneously, the multi-particle amplitudes, for example, 2 gravitons into many particles, they start to be dominated by sachurons, for which the species entropy catches up with Bekenstein-Hawking entropy. So again, this is an absolute bound possibility. So you cannot have any object for whom species entropy can exceed Bekenstein-Hawking entropy. Okay, and in particular, for example, there is a species bound in string theory. So in string theory, the number of relevant species is actually 1 over string coupling squared. Okay, and basically this is the number of elementary degrees of freedom in string theory that counts the number of decay channels of a black hole. So this may come as a surprise, because naively we may think that in string theory the number of species should be infinite, because we have infinite tower of resonances, but that's not the case, because not all of those can be treated as elementary particles. So elementary particles, for example, must have the most prominent length scale has to be a Compton wavelength, and so on. Okay, and they should not be broad resonances and stuff like this. And for example, with this taken into account, we can immediately understand the famous string theoretic relation between the string scale and the Planck scale in 10 dimensions, let's say, okay, as the species scale. Okay, and so this is sort of, the saturation is basically very fundamentally linked with this species bound, with this universal species bound. Okay.
Sorry,
Yeah.
could you go back just a couple of slides? 'Cause I'm not sure if I followed your discussion of the species scale. You said that it was for the black hole example. You mentioned something about Saturn, but I thought you were saying that it's a separate story. The species scale and the bound you got for the Saturns were separately. There were 2 different things that you were studying, right? That happened to converge. But like, can you explain again why there is this bound on the number of species in a black hole? Like,
so your question is where this bound come from? Where this bound?
Yeah. Can you just explain again what goes wrong? I didn't understand what it means for decay not to be thermal, for example, and why that is true.
Yeah, right. So for example, if you take a black hole and you just simply say, okay, let me make an assumption that this black hole evaporates semi-classically. Okay, now the black hole evaporating semi-classically has very well-defined relations between the decay rate, between the temperature and the size, the mass, and the decay rate. So they are unique relations. Okay, So therefore, if you take black hole and you say, okay, when black hole emits a particle, these characteristics change. Okay, so let's assume the black hole is semi-classical. If black hole is semi-classical, which means that we are well below the cutoff of the strong gravitational cutoff, then if black hole operates semi-classically, what happens? It emits a particle, becomes lighter black hole, and the lighter black hole has almost the same characteristics as the black hole of this mass, right? So therefore, and the temperature, the size, and the mass, they are tracking the black hole operation. All right. So now, if you take those equations and you plug them into each other, you can immediately derive the thermality parameter. Now, the thermality parameter is derivative of the temperature as compared to the temperature squared. Okay. Now, if the derivative of the temperature exceeds the temperature squared or becomes of the same order, we cannot talk about thermality anymore, period, okay? And this is precisely what happens for this size of black holes. For this size of black holes, in other words, for this size of black holes, because there are many decay channels, the black hole decays so fast that the temperature cannot catch up with the change of temperature, okay? So that's a universal criterion, and probably the simplest shortcut to see that this scale is fundamental scale. Okay, because this is derivation by the exclusion. So it's like.
I see.
Right.
Thank you.
Okay. Okay, so now let me just simply illustrate that the Bekenstein-Hawking entropy actually is a version of this entropy that I wrote. Actually, it's exactly the same entropy. It's just we never thought about this Bekenstein-Hawking entropy in those terms. Because, for example, if I have a black hole, okay, and I have an observer in asymptotically flat space, I'm considering asymptotically flat space, an observer. Now, this observer sees an object that breaks Poincare symmetry. Now, the measure for breaking of Poincare symmetry is the expectation value of the graviton field. Now, you can always go into the convenient gauge in which you can compute it, and then the result is gauge invariant because the area in those units is gauge invariant. So, and then you can see that this order parameter maximum reaches the Planck mass. And this is the property of a black hole. By the way, notice something very important, that no other object breaks Poincare's invariance at the Planck scale. It's in the asymptotically flat spaces, these are only black holes. If you have neutron star, ordinary object and stuff like that, they never break Poincare symmetry at the Planck scale. So in fact, we could have defined, we can define a black hole as an object that breaks Poincare symmetry at the Planck scale. Now, the goldstone, of course, is graviton, is coming from graviton, and the corresponding scale is the Planck scale. And therefore, if you take this into account, you see immediately that actually the expression for black hole entropy is exactly the same as for these Saturons. So in this sense, black holes are a particular example of this saturation. Now, it turns out that actually this goes far beyond, and these Saturons, in non-gravitational theories, they literally share all the properties that black holes have, all these mysterious properties. For the semi-classically, they exhibit information horizon. They decay thermally. When they are low to decay, they decay in approximately thermal spectrum with the temperature given by 1/r initially, at the initial stages. And then again, the scale required, the latest information should start coming out at the scale, which is very similar to Page's scale. Actually, it turns out the information starts to come out earlier, much earlier, could start come out much earlier, but this is a bound. So as a bound, it gives you the Page's time. Okay. So now
Sorry, can I ask one question
Yes.
about the squiggly line? You didn't put the one in the entropy of the Saturn. It was area over coupling, but you didn't put the 1/4 there. And isn't that
it's
one
actually right. Exactly. No, that's a good point. Actually, personally, I don't see much deep meaning in these 4, but actually, yes, if you normalize like this, if you take parameter of expansion that breaks these unitarities and that saturates unitarities in these multi-particle amplitudes, then yeah, it appears 4 here. Now, I don't know, if you ask me why there should be 4 and not something else, I don't know. But yes, it comes out as a 4 universally for all the Saturons in this normalization. If you normalize, alpha as an proper expansion parameter. Okay.
I see. Okay,
Okay.
I didn't. Okay.
But I don't really understand fully why why there is this 4 and not something else for the Saturons. Yeah, I understand it. So I mean, I understand this factually. I see that this is where at the point of optimal truncation, the series must be resummed, and when these multi-particle amplitudes become and so on. Okay, that I see, but that's not understanding. So yeah, I wish I could understand it better. Okay.
Thank you.
So can I ask? Yeah. So can I ask one more question? So these
Sure.
relations that you're writing are in 4D, but then the properties of Saturons also match the properties of black holes in any dimension, or no? Just
Yeah. This actually, from what we know, this is true in any dimensions. In fact, even in lower dimensions. And yeah, I will give you an example. In the lower dimensions, this thing works in a beautiful way. For example, 1 + 1 dimensional Gauss-Nievier model. I'll get there, but yes,
Okay.
the relations are universal. Yes.
Okay.
So one quick obvious question would that be, does the 4 equivalent match up in all dimensions as well?
No, that's a good point. No, I didn't study multi-particle amplitudes in all possible dimensions. No, I cannot answer that. I mean, but I think that there is always certain universal. So I would expect that there is always this correspondence between breakdown of this strong Toft coupling, the definition of strong Toft coupling, and the coefficient here. This should be universal. Now, whether this 4 will persist in all dimensions, that's a good question. Yes, that I don't know. Okay. Now, in those examples where we have explicitly matching, like in string theory and stuff, yes, it's the same. But because there you sort of already know the theory. Okay, so let me give you an example of Saturn to be concrete. So, for instance, let's take a theory with Saturn as vacuum bubbles. Okay, it's a very simple case. So let's take a theory, SUN theory with large n, and this theory, general potential. This theory, I wrote it as a perfect square. It's not a supersymmetric theory. I'm not assuming supersymmetry, but for those of you that are familiar with supersymmetry, sure, you can think of it as a scalar potential of a supersymmetric theory. Now, this theory has degenerate minima and a bunch of degenerate minima in which SUN is broken spontaneously down to subgroups. So let me pick up 2 minima, 2 neighboring ones. The one in which symmetry is unbroken, and the one in which symmetry is broken spontaneously. Okay, great. So we have this thing, and then we have this bound, so a species bound, unitarity bound on the coupling alpha. So alpha is the coupling constant, F is the scale, N is the number of basically colors, if you want, or the number of colors. So here I'm considering global symmetry for simplicity. Okay. And so this theory, therefore, because since you have different vacua, you can have vacuum bubbles. And so let's focus on a vacuum bubble. Let's imagine that we are observers. So this is radius, okay, and this is center of the bubble, and this is the order parameter phi. And so we are observers, asymptotic observers, and we see this vacuum bubble, okay, embedded in the asymptotically symmetric space. Okay, so you are in the symmetric observer in a symmetric vacuum, and you see this vacuum bubble. And in the interior of the bubble, the symmetry is broken down to a subgroup. Okay, SUN -1. So now in the interior of the bubble, you have of order n gapless Goldstone modes, okay, which do not exist outside. And now from here already you can see that the bubble can store information extremely efficiently. Okay, it can have very high microstate degeneracy. Why? Because well, first of all, you can think of the relative orientations of the expectation value, and you can store information in that. Now, this creates a false impression that actually you can have infinite microstate degeneracy. Of course not. You have to quantize it properly. And then you can count the number of degenerate microstates. And so this is the entropy of these degenerate microstates. N is the number of colors, and G is number of Goldstone modes. Okay? And you can see that the saturation of the bound that I gave happens indeed that top coupling equals 1. And in that case, the bubble behaves, the entropy of the bubble is very similar to entropy of a black hole. It becomes literally area in units of Goldstone scale. The Poincare Goldstone scale becomes equal to the scale of SUN Goldstones at the point of saturation. The radius of the bubble is given by the mass gap in the theory. Okay. Now it turns out that in these bubbles, they basically check the list of all these correspondences. Okay, so the entropy is linked; they decay like thermally, and information retrieval time and so on. By the way, this is very interesting in the sense that here things are calculable in large n. This is a renormalizable SUN theory with large n, so we can calculate everything in large n expansion, in 1/n expansion. And we can see, for example, immediately that semi-classically, if we normalize semi-classical limit, this object contains information horizon. So semi-classical limit is basically when we fix the top coupling and we take n to infinity. Okay. Also for black hole is the same thing. And so you see, for instance, that information stored in the gapless excitations cannot come out. Okay, so here's the example of information wave. So this is an information wave. So this now, it's understandable why this is happening, because there are gapless modes in the interior, and the same modes in the exterior, they cost a lot of energy. So the information cannot come out. And in the semi-classical limit, the barrier becomes infinite between the two. Okay. Now you ask this question about the other dimensionalities. In fact, so we can also explicitly calculate analog of the pages time here, and in terms of the colors are these colors basically, and so you can see that actually here it's very easy to understand why the bound is given by something like pages time, because that's the absolute time to resolve the color of the bubble. So if the bubble decays into degrees of freedom that carry color, then the time scale for decay and resolving this is absolute bound is given by that scale. So it's very similar to pages time. And by the way, I said about the other dimensionalities. In lower dimensionality, for example, in 1 + 1 dimensional, there is this beautiful large n theory, Gros-Nivier theory. So this is a very nice sort of cousin of QCD, because it's asymptotically free, theory asymptotically free, it exhibits dimensional transmutation, and it's exactly solvable in large n, okay? So there we know everything. And it turns out that we wrote this paper with Otari Sachelashvili and myself. We showed that in Gros-Nivier, where everything is known, you can just take formulas and compare. The highest bound state in Gros-Nivier is a Saturon. And all the properties of this bound state are literally in 1-to-1 correspondent with would-be black hole properties. Of course, there is no gravity, but all these features are exactly the same. Now, this brings me to the description of the memory burden effect. Okay, so now what is the memory burden effect? I told you that the feature of a system to store information efficiently, right? A necessary condition for this system to store information efficiently is that this system has to provide an environment for certain degrees of freedom to become gapless, right? In the previous example, those degrees of freedom were Goldstone modes, right? So the vacuum bubble was creating an environment in which these Goldstone modes existed, okay? And but this is universal. Now the thing is that, now suppose I have such a system, and in this system I have this gapless mode in the interior, but I don't have corresponding gapless modes in the exterior. I may have some other gapless particles, but that's not nearly sufficient. I can have some massless particles, but that's not sufficient. So now, if I have, so this is about information capacity. So we have to distinguish between the information capacity of the system, which I'm defining as the number of these gapless modes. Now, these gapless modes, I call them memory modes. So basically, my classification is like this. I say that any system of enhanced memory capacity has two types of very important ingredients, very important degrees of freedom. Memory modes, which are gapless, and they store information, and the master modes that create environment for the memory modes to become gapless, okay? Now, the important thing is that memory modes exist only in the interior of the system, whereas master mode can have partners outside. And so now if the system tries to decay, the memory modes back react, because if information load is carried, this information load back reacts. By the way, this also explains why in any system of enhanced memory capacity, at the initial stages of decay, information cannot come out. This also answers this sort of mystery. Actually, it turns out this is not a mystery. This is a universal property of any system of enhanced information storage capacity. And when sooner or later, this information load back reacts. Now, the way you can think of it is like this. Imagine you have a system. Imagine you have a room and 2 degrees of freedom. So there are the light degrees of freedom, memory modes. These are flies. And then outside, the flies do not exist. They are only elephants. And now you can store the same information pattern in flies or in elephants. But now if I store information in flies and I try to destroy the room, I have to rewrite this information pattern into elephants. But that's a huge energy barrier. I cannot do that. And therefore, I already from here, I understand the system has to back react and somehow block the decay process, okay? Now, this, we can understand this at the level of Hamiltonian very nicely. So, as I said, there are memory modes, these alpha i's, and we store information in these or patterns of these memory modes. And now the point is that these memory modes in the free vacuum, they don't exist because their gaps would be huge, or whatever the gaps are. And so the cost of the memory pattern in the vacuum would be high. But in the system of enhanced capacity of information storage, what happens is that there exist master modes. This is N phi. And the master mode creates an environment in which the gap of the memory mode collapses to 0 or near 0. So you see, if the master mode has critical occupation number, the memory modes become gapless. And information now becomes very cheap. But this also tells you that if you try to deplete the system, if you try to give away these master modes, okay, the memory pattern becomes more and more expensive. At some point, the burden sets in, and this is the essence of the phenomenon of memory burden. So at some point, at the timescale which is defined by this gap function, okay, the information pattern back reacts and tends to stabilize the system, okay? Now, we studied many prototype Hamiltonians, okay? Without any exception, always we see the stabilizing tendency. Now, okay, from here on.
Sorry, so can I ask, one quick question?
Yes.
So somehow after the page time, we think information can get out very quickly. So somehow, this memory burden effect must shut down after the page time, or it should become cheap to write information in terms of elephants or something. How does that happen? Or
yeah, okay. So first of all, I want to make it very clear that page didn't take this effect into account. So therefore, I mean, I can normalize to page only qualitatively. And one thing that I see that agrees with what Page said is that the absolute latest, by the time the memory burden sets in, is the page's time, because it's comparable, as you can see from here. So the time scale required is when the system loses approximately of order 1 of its constituents of these master modes. So it cannot continue further. Now, once the memory burden sets in, information is already readable. Okay, so it doesn't even have to get out. You can just, in other words, the system acquires features. That's the essence of the memory burden effect. Now information is readable. So you can, for example, scatter light at the system or external quanta, and you can read what is written there within very short time after that. Second point is that its memory burden effect can set in much earlier. So, for example, for most reasonable thing, the Q for Q2, Q is equal to 2, is that the memory burden effect sets in after the black hole or whatever system you have loses approximately square root of entropy fraction of its mass. Okay, so not entire, but square root, which is much shorter time scale. Yeah, so again, I mean, this is, of course, depends on this parameter Q. Maybe for black holes, mysteriously, this parameter Q is extremely high. That could be. There is no obvious reason for that. Yeah, but in any case, I mean, the pages time is the latest, and after that, information is readable. Yes.
Okay, I see. Thank you.
Okay, so now actually we can see this in this example of bubbles. Indeed, in the case of bubbles, since we said that the memory modes were Goldstone modes, if I now load the information in the bubble, the bubble gets stabilized. So here you can see two bubbles. So now both bubbles are the same. They have the same information capacity, but in the left bubble, this information capacity is not loaded. Okay, so information pattern is not loaded, and so the bubble decays much faster. And in the other, since the pattern is loaded, the bubble gets stabilized. The bubble gets stabilized by this memory burden effect. We can also see this in colors. This simulation for this bubble case. And here's a very nice video, actually, very nice simulation of this in this model. And you see literally what normally we would expect from a black hole. Okay, I mean at the initial stages. So what we see here is the following. So this is a bubble in which we have emission of energy. So this green is energy. So the bubble loses energy. Okay. The blue is the bubble shape, and red is the shape of information pattern. But it doesn't lose the information pattern. There is no red radiation coming out. So this confirms what I just said. I said that information is maintained internally at the initial stages. Energy goes out, but information is maintained internally. And at some point, this gets saturated. We enter the memory burden phase, and then the bubble gets simply stabilized. So yeah, it's the same here. Except this, for example, this is a bubble with the spin, with the angular momentum. Is the same phenomena. So we observe the same thing over and over again. Yeah, yet another. So now, okay, I will briefly mention one implication of this memory burden effect. Now, of course, so until here, there were facts. Okay, so these are everything until here was calculable and everything. Now, from here on, there is not from here on, but at this point, I will propose some conjecture. So we ask the following question. Now, what happens when the black hole encounters the memory burden? Now, the fact that it has to encounter memory burden is, to me, it's certain, because otherwise, I don't know, it's just the general nature of any system of enhanced capacity. Now, the question is, once it encounters the memory burden, and information is readable, of course, but what is the further evolution of a black hole? Now, the full answer on this is not known. One possibility which we cannot exclude is that, in principle, we cannot exclude that actually the black hole, there is some new classical instability that sets in, and black hole somehow disintegrates, or there is some classical Lyapunov exponent, very fast classical nonlinear, highly nonlinear classical decay or evolution or whatever, that we cannot exclude. But looks not terribly convincing because in prototype systems, actually the the prototype systems, they take other direction mostly. Stabilization. So what happens is that after memory burden and a possibility, the black hole just gets, the decay slows down, okay? And black hole enters the memory burden phase, continues to decay, very slowly though, okay? So the decay, the next bulk of the next decay time gets prolonged by the extra powers of entropy. Now, here n is a number which is a positive integer, because this we can prove from analyticity property of the amplitudes. So it has to be an integer, and so it starts from 1, and then, okay, what we don't know how big this can be for black holes. For prototype systems, we can calculate, but and in any case, so this is the story, and of course, this has very interesting implications for primordial black holes as dark matter, because previously people thought that the primordial black holes lighter than 10 to the 14 grams or something like that, or 10 to the 15 grams, they are not interesting because they would be gone by now, because people were naively extrapolating semi-classical regime all the way, okay? Yeah, instead what we are saying is that they can be happily be around and be in the memory burden phase, and they can be an absolute legitimate dark matter. They can be dark matter. There are certain very interesting predictions coming out of this because, for example, they must have, because the stabilization happens because of the information load, there must be a model-independent spread in masses. Even if your production mechanism at the initial stages was monochromatic, there are interesting spread of masses predicted, okay, and so on. Let me do this. Yeah, let me just show this example. And also they can be very interesting source of very high energy cosmic rays, in particular neutrinos. So we wrote recently this paper with Sebastian and Michael. Actually, yeah, it's an interesting potential fit in the high energy neutrinos of ice cubes, seen by ice cubes. But it's a general message. So in general, the memory burdened primordial black holes, they can be very interesting source of black hole dark matter. Okay. Now, since I don't have time, I will make a shortcut right to the de Sitter story. But actually, I can just mention that. Yes.
Yeah, sorry. So can I interrupt you one more time? Yeah, sorry.
Sure.
So the timescales that you showed were all much longer than the page time, right? Like so R to the S 1 plus N.
No, this is not. Yeah, no, this is not. No, this is not the time scale. So this is post memory burden lifetime.
Oh, this is post memory burden.
Right.
Oh, this is lifetime after you.
After the memory burden. Right.
So at what time does the black hole get to the? So, but I guess you were saying that the memory burden effect kicks in before the page time.
Exactly.
Right?
Well, the page time is the latest.
Is the latest, yeah.
The latest, right. So as I said, we don't know this precisely because this depends on the power that enters in the gap function. We don't know precisely this gap function for a black hole. We know what the modes are. We know what the memory modes are. We don't know what the precisely gap function is. I don't see a reason why Q has to be much larger than 2. And if Q is 2, then the memory burden phase will happen for much earlier than the page's time. It will happen when the black hole will lose approximately square root of entropy fraction of the mass.
I see.
Okay. So, but again, this is an open question. So no, with page, there's not, so later than page, nothing can continue. So this is also what we see. Yes.
I see. Okay. Thank you.
Thank you. No, this is. Let me go straight to the point. Now I said, yeah, there was this thing about there is yet another mystery of black hole physics, which is that black hole, well, mystery. We know that semi-classically black holes that spin faster than their entropy do not exist. We know semi-classically this is true, but we don't know why. And actually, it turns out that this similar feature is developed by Saturons in non-gravitational theories. But there we know why. So it turns out that if you try to take Saturn, for example, this vacuum bubble that I showed, you try to spin the Saturn higher than this bound, what happens is that by the time you approach this maximal spin, internal vorticity develops. And beyond that, the vorticity takes up all the energy. So you need to pump more energy into the Saturn and correspondingly increase its entropy. Okay? And then we speculated maybe this is a similar thing that is happening for black holes. We don't know. This is a speculation. I want to make it very clear. But if it is, then it's interesting that there must be different regimes of gravitational radiation from merging black holes. So this is green regime in which merging black holes do not produce vorticity because they don't spin sufficiently. Then there is another regime, red one, in which they produce vortex, and then it gets ejected, and then the output is delayed. And then finally, there is a third regime in which there is an internal vorticity kept. And so in that case, the energy output is very little. So this is interesting because this is, in principle, macroscopically observable features, that can be looked up in gravitational radiation. Okay. Okay, so let me go to de Sitter in the remaining 7 minutes or something. So another object of maximal information storage capacity is de Sitter. Okay. So the question is, what is the implication of the memory burden for de Sitter? So we had this proposal that also in de Sitter there must be some sort of a memory burden effect. Now de Sitter has this very clear-cut indication that it has degenerate microstates because it has Gibbons-Hawking entropy given by the area. Very similar expression for a black hole. But now the question is, what is the meaning of the memory burden in de Sitter? How it is related with Bekenstein-Hawking entropy and so on? And let me discuss one aspect of this, okay, which is related with one aspect through string theory, okay. Now I have this I don't know, I have this proclamation which I'm pushing for many years, that we cannot have de Sitter in string theory or in quantum gravity. We cannot have like what we call real de Sitter, I mean eternal de Sitter in string theory or quantum gravity. And the main reason is the S-matrix formulation of the theory, because string theory is manifestly based on S-matrix. So de Sitter should not exist there. But let's try to understand, maybe string theory itself tells us first, why this is so hard, and secondly, maybe this sheds some light on the Gibbons-Hawking entropy. And now, since we have this feature of memory burden, let's see if we can get some mileage from there. Okay. And so here's the point. Okay, suppose we want to construct de Sitter in the simplest possible way in string theory. Of course, we're going to fail, but we're going to fail in very extremely interesting way. Now, let me do this. So in string theory, this is the old story that goes back to Henry Tai and my work, because we had this question, how to get de Sitter in string theory or inflation. And then we said, okay, I mean, you need objects with negative pressure. And the only existing objects with negative pressure in string theory are d-branes. So you need d-branes to somehow get de Sitter in string theory. So now, so you need this. So basically, we introduced this idea of d-brane, what people call now d-brane uplifting. Sometimes it's called. Okay, so now let's try to do this in a simplest possible setup. Okay, let's say in 10 dimensions in type 2. So we have d-branes, and we put on top of each other a bunch of d-branes and anti-d-branes. Now, so I keep putting on top of each other d-branes and anti-d-branes, and of course they have tension. Because of this tension, if the system would be stable, if I imagine for a moment that I'm a classical observer and the system is stable, okay, then there would be de Sitter's geometry responding, and there would be corresponding Gibbons-Hawking entropy. Okay. Now, this Gibbons-Hawking entropy and Gibbons-Hawking temperature. Okay. Sorry. First, Gibbons-Hawking temperature. Okay. So we will arrive to the entropy. Now, the Gibbons-Hawking temperature, what it would do, it would excite open strings. Okay, so now if I put n d-branes on top of each other, I have open strings that connect them, and they become gapless because when I put them on top of each other, and I get n square of these Chan pattern factors. Okay, of this n square of this Chan pattern species. Okay, very good. Now, this n square of Chan pattern species, now without considering this would be Gibbons-Hawking entropy, there is an instability because de Sitter would simply, the branes and anti-branes, they would annihilate. So this can be described as tachyon condensation, right? As Sen and others were describing it. So it's a tachyon condensation. But what happens is that because of if we take into account that there is a temperature in this Chan pattern species, then they create the memory burden effect. So basically, Chan pattern species create the memory burden effect on the tachyon, and then they tend to stabilize the tachyon. So now the question is, okay, is there a limit in which the tachyon can be stabilized? Because if we can do that, then we have full-fledged de Sitter. Well, it only happens in the limit, so it's very interesting. This happens in the limit, but actually doesn't happen because precisely in that limit, the theory goes out of validity of the geometric description. But it's still very interesting because what happens is that if we take this Toft limit and we take the limit when we take the limit in which we want Gibbons-Hawking this memory burden from species to compensate the mass of the tachyon, then in that case, the entropy of Champaton species entropy, precisely matches what would be the Gibbons-Hawking entropy of the space. Unfortunately, precisely at that point of matching, the theory cannot be trusted anymore, the geometric description, because the curvature becomes afforded the string scale. So we are entering some Hagedorn phase or something. But nevertheless, this is still extremely instructive because I consider this as basically I think this is as good as it gets as far as derivation of Gibbons-Hawking entropy in string theory is concerned, okay? Because simultaneously, it's very interesting because string theory at the same time tells us that the de Sitter is not welcome there, but at the same time tells us how to think about de Sitter Gibbons-Hawking entropy within the string theory, about the would-be de Sitter Gibbons-Hawking entropy. So yeah, that's basically the point. So that's in that limit. This is precisely, by the way, the limit in which we saturate species bound when the number of Champaton species would saturate the string theoretic bound on species scale. And so yeah, that's where the matching happens when the species entropy and Gibbons-Hawking entropy become equal. Okay, I think I should finish because this is already 1 hour. Okay, so maybe I'll finish with some outlook. Now, okay, there are few points, few messages. Okay, this is a program that I've been developing for many years, and obviously, okay, a lot of different things accumulated, but I tried only to discuss the things that are really interconnected. And so we see this interconnection between saturation, this universal property of saturation, and saturons. They have these universal properties of black holeness. So probably what we are observing is that at least huge part of black hole properties is not necessarily coming from gravity. It's not really gravitational, but it's more general. Okay, it comes from saturation, and those systems also, they exhibit this universal phenomenon of the memory burden, and it sort of works in two ways. Okay, so these saturons are very interesting because on one hand we can understand these mysterious features of black holes in very clear way in calculable theories. At the same time, we can see new features like this memory burden effect, which now can go back and explore in black holes and in de Sitter space. Okay, let me finish here, and I'll be happy to take if there are more questions.
Okay, thank you very much for that very interesting talk. Are there any questions from the Zoom audience out there?
Can I ask a quick question?
Yes, please.
Yeah,
Yes,
so I understand that this memory burden effect in some sense is stopping the black hole evaporation because of these modes that store the information and are gapped. But does this also prevents the black hole from like fragmentation?
Yeah, very good point. Yes, actually, that's what I essentially said. I said that we cannot exclude something what you call fragmentation in principle. Okay. So we cannot exclude that this is what will happen. So in other words, there is I don't have any proof against this scenario that the burden sets in and then something very dramatic because the Lyapunov exponent sets in and some very dramatic decay happens, like what you said,
Yeah.
sort of fragmentation and nonlinear effect. Yes, that is a possibility, certainly. Yes.
Okay. So I guess at some point this fragmentation should also stop because you would reach sizes of objects which are near the cutoff scale also set by the
Yeah.
species bound or something like
No,
that?
absolutely. No, that's correct. So of course, all this discussion applies only to the objects that are sufficiently larger than the cutoff scale. Of course, absolutely.
Okay, fair enough. Yeah, thank you.
Once we approach the cutoff scale, of course, we need the theory that controls strong gravitational effects. The same happened in de Sitter. In de Sitter, the reason why this derivation that I'm giving of Gibbons-Hawking entropy cannot be fully trusted, only understood as a limit, as a very interesting hint, but because precisely in that limit we are at the string scale. So, and then of course geometric description breaks down, as we know. Yes, absolutely, I fully agree with that.
I see. Thank you.
Any other questions?
Can I ask a question?
Yes. Sure.
So this matching with the area law of the entropy, can we? Yeah. Do you try to extend this beyond the leading term? For example, in semi-classical calculation, you can calculate some log area term, and yeah, do you try to match it?
So to match it to what? To the subleading corrections?
Yeah.
Subleading corrections are actually, for such ones, they are much easier computable because you don't have to think, because you know the theory. And they essentially come from the quantum corrections to alpha. So on these subleading corrections, they come from the quantum corrections to alpha. So there it's like, it looks pretty. Now, in case of a black hole, of course, these subleading corrections, they can be interpreted in different ways. Sometimes these subleading corrections you can also absorb into sort of corrections to either Newton's constant or to Casimir energy and stuff like that. But yes, you certainly have.
But there are some more unambiguous part, right, of the semi-classical answer. These log area corrections, right? For example, computed by Sen, Sen, for example.
Yeah.
Right. Those type of corrections are more robust, right, to try to match.
Yeah, I'm saying, no, that correction is fine, but it's a question of interpretation, right? So certainly that calculation is I think it's perfectly fine and correct. But then the question is, maybe you can interpret it in some way. You can ask, right? You can say, okay, maybe I can think of this as some sort of Casimir energy of the cavity, okay, correction to it, or maybe I can think of it as correction to G Newton, or as correction to black hole mass, and so on, right? And for that, it's useful to have a renormalizable counterpart in which those corrections also exist, but their theory is renormalizable. So there, we know what we are talking about. There are only finite number of renormalization effects. This matching of the full program of matching one to the other, I have not done. It's interesting to take. It will be interesting to take it up. Yes, for example, in Gross-Nivier. Now, of course, in Gross-Nivier issue is that, Gross-Nivier is in 1+1 dimensions. It behaves like a would-be black hole in 1+1 dimensions. It continues all these features. But to match it with, you need to have some black hole counterpart to match with. And in 1+1 dimension, black holes are not so uniquely defined. You can have black hole like objects, but they're not uniquely defined. But anyway, so yes, this program of trying to compute corrections there and try to understand this in terms of map it on the corrections from the black hole side. Of course, this computation by Sam, it's fully semi-classical. It's fully semi-classical, and what we see actually there are corrections of 1/S type, okay, to the black hole physics. Also, which semi-classically cannot be captured because in semi-classical limit, entropy goes to infinity. Black hole size is kept finite, but entropy goes to infinity. Anyway, so there are all these, there are all these interesting questions. Thanks. And also in this discussion, I meant like, of course, there are different things. People here in this audience worked on de Sitter entropy or de Sitters in the quantum gravity and stuff like this. This is it's sort of these views could be complementary, but here the reason is that we have a very concrete microscopic phenomena. and it's a universal and very concrete microscopic phenomena. So it looks like it should be equally applicable to all these type of systems, right? Black holes, the sitter, and so on. So yeah.
Thank you.
Can I ask a question? So, well, okay, I have a very naive question. So, in the context of holography, the way we get area over 4G Newton is just to count the high energy density of states
Yes.
of an ordinary quantum system. And for example, the Carty formula of a 1 + 1 DCFT produces the Gibbons-Hawking entropy of 3D BTC black holes, for example. And there, would you say that the holographic dual description is just a different description, or is there any relation between this kind of Saturn picture that you're talking about, the memory burden effect, for example? What does it look like in the dual CFT?
Yes. Yeah. So of course here, so there are several important points in your question. Okay. So of course, as I said here, I'm not proposing duality between the theories. I'm not saying that the theory of a black hole is dual to another theory which also has a saturon. That's not what I'm saying. I'm saying that in both theories and in essentially all of those theories, there exist very special states, and those states exhibit similarities. Okay, so this is not duality between the theories. Now,
okay.
however, if I will zoom down my Hilbert space around those very special states, yes, then around those very special states, it looks like, because, for example, saturons, they are also because the memory modes become essentially gapless in large n limit, right? The gaps are like 1/n. Yes, they admit some CFT type description, at least approximate up to 1/n CFT description. Now, yes, those CFTs, they can happily be related, because after all, they are all CFTs. With the essentially they have common central charge once you normalize it. Yeah. So yes, those could be related. Yeah. And I think that's natural. So in that, I would not see any surprise in a sense, because once we have an object that admits some sort of CFT description in the neighborhood of this Hilbert space, yes, then the similarity is also there. Now, of course, what can be different in gravity, which is not the case in other saturons, is that, for example, in gravity, you may have some entire theory which is dual to it, in principle. Okay, so then that's a separate story. So I'm not now. We have very interesting examples of that we think they are saturons. For example, Raju Vanugopalan and myself, we wrote a paper pointing out that the state in QCD, the so-called color glass condensate of gluons, is actually like a black hole, and it's a saturon basically. Okay, so it has all these features that are very strikingly similar to a black hole, and so on. Yes. So yeah. So now, question about holography. Yes, for me, it depends how we define the holography. So if we define holography in the sense that, in very general sense, in the sense that once I'm approaching the saturation point, the effective theory of memory modes can be described as some sort of CFT. I think that's common. So I would expect that to be common. Now, however, if we want to define holography in the way that necessarily those modes that carry information, they have to be necessarily crowded on the surface of the object, okay, that what we are discovering, that's not necessarily true. So in other words, you have saturons. For me, all saturons, their entropy scale like area. The reason for that is that the Goldstone coupling, actually, it's good that you're asking this question, I forgot to mention, that Goldstone coupling has this property that universally scales like area. So the inverse of the Goldstone coupling always scales like area, in any dimensions. So if we are asking, for example, if I'm looking for Goldstone scattering, and I'm asking what's the effective coupling at the momentum transfer 1/r, the effective coupling is r squared, precisely that expression. So therefore, what the area we see, because it's a Poincare Goldstone that controls it, and its coupling is like area. By the way, similar to graviton coupling. Actually, graviton coupling also scales like inverse area, very similar to Goldstone coupling. So therefore, entropy scaling is universal area, but we see examples, explicit examples, where the modes are not necessarily populating the boundary. However, okay, in this when I gave you these videos, you may notice that there was this sort of boundary, yeah. For example, these ghost-town modes, once they were populated, so this sort of this information pattern, yeah, was creating this impression that as if it sort of wants to be crowded near the boundary. Okay, so yeah, so sort of the shapes are sort of as if they want to be near the boundary. Yeah, I don't know whether that's a holography in the full-fledged holography, but yeah, but there's also this feature. Yes.
I see. So you're not placing this story within the paradigm of the holographic principle that the host and Susskind were advocating, which is
So sorry, which paradigm?
The Satyron, the idea of that the black hole is like a Satyron and its information processing behavior can be understood purely in terms of properties of Satyron.
Yes.
That's a separate paradigm than the holographic principle, which says that.
Yeah, not necessarily contradictory. Yeah. I mean, it's for sure. Yes, it's a completely separate paradigm because I'm arriving there from very basic quantum field theoretic questions. I'm asking like very basic questions. I'm saying, okay, you have quantum field theory, well-defined degrees of freedom, well-defined coupling, running, everything could be renormalizable. And the question, what's the maximal microstate degeneracy? And this is a fully answerable question. And this is the way we arrive there, right? Now, whether this excludes the other paradigms, no, not necessarily. I think at some point those paradigms could even merge. I mean, that's I would not claim that this is incompatible with holography. Now, what I would not agree with is this is not black holes, but sometimes people say, oh, there is this general feature for any system that information is always, it can be always stored on the boundary. Yeah, that I don't know if I would necessarily subscribe to that, because we see that this area scaling of the entropy is an exclusive feature of saturated objects. So the ones that really saturate the bound. If I have a generic object which is not any close to this saturation, there to claim that the information should scale like area or something, no, that's not what we see. I mean, that's yeah. So therefore, for black holes, sure, yeah, absolutely. For black holes, that's a fact. That's correct, yeah. But
I see. Maybe my final question is then, what is special about a black hole? If these properties are not special to a black hole, then, I mean, for example, one would have thought diffeomorphism invariance in general relativity is something special, and it suggests why the theory might be holographic, because you can't define a point. There's no local operator, right? So somehow it wouldn't make sense to say that there's as much information as there is kind of space-time volume. And that's why holographic principle seems to make sense, at least to me, right? But now you're saying that these area laws come out of the ordinary QFT, not out of gravity. So then what is special about gravity in your
right? Right. That's a fantastic question, and I can give you my version of the answer. So there is yet something special about gravity in the following sense that it is absolutely true that I could not identify any property of a black hole, any known property of a black hole that would not be exhibited by Satyrons. I don't have such property on my list. But there is the following difference, that gravity can produce Satyrons at any scale, because black holes of all possible sizes exist in gravity. Now, in generic QFT, the Satyrons may be special points. So it doesn't mean that if you have Satyron of a given size and given mass, you necessarily have Satyron of arbitrary size, okay? So in other words, the spectrum of Satyrons itself spectrum of each saturon is highly degenerate, but the spectrum from saturon to saturon, that is a theory dependent, okay? Now, in gravity, we always have this, that in gravity, the spectrum of saturons is continuous. So you have saturon for every black hole, okay? So yeah, that's the difference. And that is precisely traceable to the diffeomorphism invariance and the spin 2 structure of gravity. Yes, that is property of gravity.
I see.
So the abundance of saturons is a feature of gravity.
I see. Okay.
Gravity provides saturon for any given size, for example.
I see. Okay, well, thank you very much for indulging us in a very interesting discussion. Unless Clement and Ludo have some extra questions, I think this might be a good time to
Yes.
wrap. And